Thanks a lot.
No problem.
Thank you very much. Okay, that I didn't switch off that audio.
Yeah, so audio you have to
Switch off and start from
and
here.
then start it again.
Can you people hear me?
Yes, ma'am.
And can you see the board?
Yes, ma'am.
Yes. I tried to do independently. That's why it took a little time for me to start the meeting. Okay. So let me continue with my lectures on group theory. Okay. Before because I might forget, I know you people have exam on Wednesday. So one thing which I can ask is that Monday can I take the class? I won't take on Tuesday, but at least Monday can I take a class?
Okay, ma'am.
Monday morning, what time? You tell me which time is convenient.
Ma'am, 11:15 to 12:15.
A little bit more time because I would like to finish on that day. Monday, and then I'll take finally on Thursday.
Ma'am, because we have MEP lectures from 10 to 11 and then special subject lecture from 12:30 to 1:30. So
I see. Okay. Afternoon is not possible. You want to study. Okay. So 11:15 to 12:15. 11:15 to 12:15. Fine. Monday. All right. So yesterday I gave you an idea of what are groups. So we defined what we mean by a group. And then after that, I gave you some examples of some groups. So then I was trying to describe the various kinds of groups you can. So we had finite groups. So finite groups means the group essentially consists of only a finite number of elements. And then if I have an infinite group, it has an infinite number of elements. And infinite groups you can have among infinite groups, particularly interesting are those which we call as a continuous groups. So continuous groups means the group elements are parameterized by continuous parameters. Okay. So I talked about this. And then further I was going to tell you about. Okay. So I was giving you this example that consider this group, which is made of these elements 1, I, minus 1, minus 1. So you can see that it has 4 elements and the group operation is multiplication. So usual multiplication. And you can verify for yourself that this set of 4 elements, and if you define the group operation to be multiplication, then in that case, this satisfies all the properties of the group. And now if I consider this subset, so consider this particular subset, 1 and minus 1. And with the same group operation. What you can see is that if I take this subset, again this subset forms a group. Because with just these 2 elements, which we saw already earlier, what I was calling a Z group. So this again forms a group. So often it can happen that you can get a subset. So given a group G, they can be a subset of the group in such a way that all the elements, if I just consider that subset, that itself satisfies all the group properties. Okay. So a subgroup means it's a subset of a group satisfying all the group properties. And when I say satisfying all the group properties, please remember I cannot change the definition of the group operation. It is with the same group operation. Okay. So we define a subgroup. So given a particular group, I can have a subgroup, which is basically some subset of the group in such a way that the elements of that subset all satisfy these properties and with the same group operation defined. Now, most generally given any group G, you will have trivial subgroups. So always you will find 2 trivial subgroups. And what are the 2 trivial subgroups? One is that if I take H to be as the identity. Note that in any subgroup, the identity must necessarily belong to the subgroup, because if you don't have the identity, then the third property of the group will not be satisfied. So, suppose now I consider a subset of this any group, and you just consider the identity element, then it is trivially a subgroup. Similarly, if I take H equal to G itself, so these are the trivial subgroups for any G. So for any group G, I can take the group itself. Obviously, that is again a subgroup. So any group G will have two trivial subgroups. One is a subgroup containing only the identity, and the other is just the group itself. And any other non-trivial subgroup which is not either of this is called a proper subgroup. So proper subgroup is one which is not identity or G itself. So for example, if I go back to this example, when you had this 1I minus I minus 1, let me use the notation which I had earlier. If I call this as Z4, we'll see why we call this later. And if you take this particular subgroup here, or this particular subset, this forms a non-trivial subgroup of this group, and or therefore it's called a proper subset. And we also discussed what we mean by an abelian group, what we mean by a non-abelian group. So yesterday I told you that abelian group means if under the group operation, under the group operation the combination is commutative, if it commutes, then in that case you will say it's abelian. That means G1 dotted with G2 is equal to G2 dotted with G1 for any G1 and G2. Then in that case I will call it as a commutative or an abelian group. And if it doesn't satisfy that, then we call it as a non-abelian. Now further we can let me keep this example. Now for a finite subgroup, for a finite group, as I said, a finite group essentially means that you have a finite number of elements. And suppose, let us say I have a finite group, and let us say I have G1, G2, Gn. That means I have n elements. So the number of elements in the group, okay, I will call order of a finite group. We define something called as an order of a finite group, and is equal to the number of elements obviously this makes sense only for a finite group because that's going to be a finite answer. Otherwise it's going to be infinite. It makes not much sense. So for example, if I take this particular group Z4, then in that case my order for the group is 4. On the other hand, if I take Z2, which is simply 1 and minus 1, then the order is 2 for the group. Now I can also define order of an element of a group. See, whenever I have a finite group, you can see that if I'm combining this, suppose I do G1 dot G1, okay, under whatever is the group operation is this. Now this will give you some element of this, and if I do it sufficiently a number of times, I should finally get back an identity. So if you have that, say G1, G1, G1 for any element, okay, suppose I find that for an element, so I combine it n times, and if we'll see examples in just a while. If this is equal to the identity element, okay, then we will say that m is the order of the element. That particular element, the element. For order of identity is always taken to be 1. So order of identity element is by definition this one. Okay, now let's go back to this example just to illustrate. So here you can see that the order of this group is 2, order of this group is 4. Okay, now let's look at these two elements in this group. I have the identity element and -1. For identity element, so order of 1 is 1 by definition because it is the identity. On the other hand, if you look at order of -1, what will that be from this definition? Can you tell me?
2.
2. Yeah, you can see that it's going to be 2. Okay. If I go to this now, what will be the order of 1? By definition, it's going to be 1. For I, what will be the order?
4.
Okay. And for -1?
4.
And for -1?
2.
So what you can see from these two examples is, if you look at this, that you have for identity it's 1, for -1 it's 2, and for I and -I, the order is 4. Where the order of the group itself is 4. Okay. And in general, you can show that this order of any element cannot exceed the order of the group. So the order of each element will essentially vary between 1 and the maximum value will be the n, which is the number of elements. And very often, okay, now I will try to do another kind of group. So basically what we are trying to do is trying to introduce you to different concepts associated with groups. Because these are of use for us. All right. Now, very often it will happen that I can make a group. So suppose I make a group with just one element, one non-trivial element. That means say I can make a group with, let's say I define a group like this. Say its identity is there and then one element is there, G squared and that's up to G to the power n. So Gn is equal to 1. So what is the order of this group, by the way? So I have only one non-trivial element, which is G. I'll give an example in just a little while. And I have built the group with this all these elements. So it's 1 G, G squared, G cube up to G to the power of n minus 1, G to the power of n is 1. Let me put this in here. So now what is the order of this group?
N.
N.
Yeah, and what you, okay, so this group is, if you can build a group like this, okay, a group like this, because you can see that I have multiplied, okay, look at the structure of this. I have one with G will give me G, then G with itself gives me G squared, then the next element is G cube, which will be G with G squared. When I say these things, okay, so when I write G to the power of n, I'm not told you actually what is this. Okay, so this is, it need not be, so this is n times, okay. But I'm not told you what are the elements with some group operations. Okay. So I do this n times a group operation. So here now, if I combine 1 and G, I will get G. If I combine G with itself, I'll get G squared. If I combine G squared with G, then I'll get G cube, and so on. And now you can see that if I combine G to the power of n minus 1 with G, I will get back. So such a group, therefore it's called actually, such a group is called cyclic. So for example here, this group, look at this. Here you have the identity and now your G is nothing but minus 1. So this is actually a cyclic. So this is a cyclic group of order 2. This is also a cyclic group. So the way I will write it is now minus 1 minus. So you can think of G as equal to I here. Okay. So you can see 1 into I will give me I squared is minus 1. Okay. Then I cube, if I take, I will get minus I. And then if I take minus I to the power of 4, I'll get that. So both of these are examples of subgroups. Again, as I said that we will also have these in physics applications. We will also have reasons to deal with subgroups. So now before I go further,
Excuse me, ma'am.
yes. Yeah.
Ma'am, then according to this definition, then any group of order 2 with one element 1 will be cyclic group.
Yeah. Okay, that is right. That's good. That's a good observation. So we can ask now. That's correct. So in fact, now I can ask this question, and I'll do it a little later before I give you some more examples. First, I do. But so I can ask the question now. Suppose I have this group G, which is equal to say minus 1, 1, 1, minus 1. And now let us say I have another group G prime, which is say G1 and G2. Okay. Because this has only two elements, G1 and G2. And here with this is dot equal to multiplication. So I can ask now the question. This is also a two-element group. There is some dot here which is satisfied. So now I can ask the question that is, can I connect this? Because as she put it, that any group must do, if the two elements are just two elements are there, then I should be of this form. Now what we will see is that I could have some other elements, but I can have a mapping from here to here. Okay. So I'll just deal with it in just a little while. So before I give you examples, and I want to give a little bit more abstract examples, and then after that I will come back to your question. But that is a very good observation that you made. Because now I want to, okay, I'm going to give you two more examples. And the reason I'm making these examples is that I want to show you now that the group elements, we can think of this in more abstract ways. So far I've just given you with some numbers. Then we saw the matrices multiplication, matrices and matrix multiplication. But now I want to deal with an example where a little bit more abstract way of defining a group. So again, let me go back to this. So let's consider now, suppose I have an equilateral triangle. Okay. And let the vertices be ABC. Okay. And imagine that you're in this two-dimensional space, these vertices are fixed. And I'm also going to label these by 1, 2 at these corners. Okay. So imagine that I have got this in this board, which is this two-dimensional space. I fix this ABC, and then I place something which labels 1, 2, 3 at these vertices of this equilateral. Now let us ask, what are the two-dimensional operations? So all the possible operations all So I want to ask, before I will place this a little later, we'll place it back. I have this equilateral triangle and I want to do some transformation on this equilateral space. Okay, such a way that this equilateral triangle remains the same. Now, can you at least tell me at least one transformation which I can do on this?
Rotation.
Rotation, but any arbitrary rotation, will it keep it like that? See,
120 degrees.
120. Okay. So, and rotation, see, when I talk about rotation, I cannot simply say 120 degrees, right? I have to also give you what other thing I must specify. You have specified the angle by
I'm keeping
Axis of rotation.
one vertex constant.
So, what is the axis of rotation? When you say 120 degrees, what axis I should rotate? See, I must keep the same shape. I can't change the shape here.
Axis perpendicular to the plane of the triangle passing through the centroid.
So you look at the centroid. So if this is my centroid, take the axis perpendicular to this. So that means it's like coming out of the board. And then what I do is I can rotate by 120 degrees. Now when you see I'm doing about, so imagine that I'm doing about this axis. So it's perpendicular. So this is my axis of rotation. But you can see now I still have some freedom. I can rotate about 120 degrees like this or like this. I can rotate clockwise or anti-clockwise. Isn't it? So it's not enough to specify just 120 degrees. I have to specify whether I'm doing a clockwise rotation or an anti-clockwise rotation. So if I do a clockwise, let's call that as 120 degrees. Then you can see that, okay, now I do back this 1, 2, 3. So suppose I do a clockwise rotation, an anti-clockwise rotation. So an anti-clockwise rotation about O. I'm writing it very basically, and when I'm saying anti-clockwise, it is like from the way I see it. It's on the board. By 120 degrees is like 2 pi by 3. Okay, about an axis through O. And perpendicular to the plane of the triangle. Right? Then what will happen is that you can see that when I make this rotation, C will go, this will go here, this will come here, this will come here. So if I look at these points, so I imagine that I don't do anything to those ABCs. So I keep it as ABC. But what will happen is that my 3 will go to 1. I will get here. Right? On the other hand, if I did a clockwise rotation, what will happen? Suppose I did a clockwise rotation by 2 pi by 3. Then how will it go? What will change here? Again,
3 will go to B.
but no, you imagine that ABC remain. Don't change ABC. Only change those inside points.
3 will go to B, 2 will go to A, and 1 will go to C.
So 3 will go to 2, 2 will go to 1, and 1 will come to here. Correct? So in that case, what will happen is that, so don't change the outside one, just change this one. So this will come here. So 3 will come here, 2 will come here, and 1. So you can see that by making clockwise rotation and anti-clockwise rotation, if you look at those 1, 2, 3, those have changed. Because in this case, what I've got, so first it was 1, 2, 3. Now this has become 2 here, 3 here, and 1 here. So if I'm looking from this way, it's 2, 3, 1. On the other hand, here it is 3, 1. So whether I make a clockwise rotation or whether I make an anti-clockwise rotation, these are giving me 2 different operations. And you can also see that this is the same as, see, because I'm doing 2 pi by 3 like this. That is the same as clockwise or anti-clockwise rotation by 4 by 5. But anyway, let's leave it like this. Okay, I will just write it like this. And let us give a name to this. So let me call this as R, okay? Because I don't want to write this so many times. And let us call this as R. Fine. Now consider this thing. So I'm just considering these transformations, R prime. Now, is there any other transformation which will leave this equilateral triangle invariant? Are there any other transformations?
Interchanging the vertices.
Okay. How would I interchange the vertices?
Reflecting about the perpendicular bisector of the
So
side.
for example, what I can do is, say, for example, I can do like this. So suppose I construct, I have ABC here. Okay, let's just do like this. So I have ABC, okay. And let us say that I have this perpendicular bisector. Let me call this as say N. AN. And what I do is now, so construct the bisectors from this vertex A to, perpendicular to this. Now what you do is reflect about this bisector. Okay. So reflect about AN. What will happen? So this is 1, 2, 3. What will happen? So reflect about AN. What will this go to this? Again, I'm going to get this equilateral triangle, ABC. So again, I don't want to change this, but inside what will happen when I do this reflection?
Angle
3 will
2
go
and
to
3 will interchange.
1 will remain the same now, but 3 and 2 will get interchanged. So you can see that I will get 1 here, and now I will get 3 here and 2 here. Right? And let me call this as L. Okay? This operation is this reflection operation. Similarly, what I can do is I can define, I can reflect about B, let's say, the bisector like this, and let's call that as M. Let's call this as A. Doesn't matter. A. So let me call this as L. Now I can do a reflection about. Okay, so I reflect L equal to reflect about BL. Again, I have 1 here, 2 here, 3 here. Now what will happen? Which will get interchanged?
One and 3 will interchange.
1 and 3 will interchange because you can see that 2 will remain fixed, so 1 and 3 will get interchanged. So what I will get is now A, B, C. 2 will remain the same. This will become 3. Similarly, I can do now one more operation, and that is reflect about this particular bisector. Okay. Again, I have 1, 2, 3. And now you can again see that 3 will remain fixed, but 1 and 2 will get interchanged. So I define this N as equal to reflect about C. Okay. And what I will get then is when I do reflection about this, 3 will remain this, and this will become 1. So if I consider now the set, remember now I'm just considering the set of all such transformations. So I've given the names to this, so let's consider R, R prime, K, L, M. And let me also consider a null operation. So the null operation is the following, or the null transformation, where I do nothing. So I have ABC, 1, 2, 3, and I do nothing here. So what do you think I should call this as? This transformation, where I do nothing.
Identity.
Identity. So call this as the identity transformation. Now consider this set, which consists of these two rotations, then these reflections about these perpendicular bisectors to each of the vertices, and the identity transformation of the null transformation. Now, are there any other transformations which leave this equilateral triangle in the end? So you can show for yourself that there's nothing else I can do. Any other transformation can always be written as a combination of these. In the sense that, see, now what I can do is now let me define the group operation in the following way. So consider this set now, and then what I will do is the following. So let me remove this. So I'm going to consider now two successive such transformations. So suppose I have R and R prime acting on this. So let's say that I have this, I'm putting this dot and ABC here, 1, 2, 3. So the way I'm going to define the group operation is the following way, that if I have R dot R prime acting on this, is by definition R, then first of all I do R prime acting on this. So I remove this ABC now because these are actually identical. So it's have 1, 2, 3. Okay. So it's first on this. So on R prime on this, we have seen already that if I do R prime on this 1, 2, 3, it goes to 2, 3, 1. I'm always going from here like this. So this goes to 2, 3, 1. Now R acting on this, what should I get? R, remember, is this one.
Identity.
How will I get identity? Yeah, you tell me how.
The same equilateral 1, 2, 3.
Because you can see that now if I do R on this, 1 will go to 2, 2 will come to 3. Oh, sorry, 2 will come here and 3 will come here. So I'm going to get here 1, 2. Which you can see is nothing but identity acting on 1, 2. But this is how I define my group operation. That first I perform this transformation, then successively I do the next transformation. And you can see now that if I do first R prime and then if I do R, then I'm going to get back the identity. And that is quite obvious because I first done a 2 pi by 3 rotation clockwise. Or R prime I did with R prime is clockwise. So I did a clockwise rotation first, then I'm anti-clockwise I'm doing. So obviously I should go back to my original position. Now suppose instead I do an R and a K, what will happen? On 1, 2, 3. What will this give me? You've seen that. So again, by definition, this should be R times. So R I'm going to do. First I do K. So K on 1, 2, 3 will give me. It will remain, 1 will remain fixed and 2 and 3 will be changed. So I will get here 1 and 3 and 2. Now if I do R on this, what will I get? What will this give me?
Angle A will be equal to 2, angle B will be equal to 1, and C will be equal to 3.
So it's going to become 2, 1, 3. Agreed? Because you're doing a rotation like this, you can see when I do R, what is happening? If this is going here, this is coming here, and this is coming here. So 2 should go to 1. When we will come in this A position, this will come here, this will come here, so it becomes to 1. But when do I get? Can I write this in terms of anywhere else have I got this? You can see that this is what I get. So this is like R prime acting on 1, 2, 3. So R dot K is nothing but R prime. Can you see that? So first reflecting, so if you want to understand this, so reflecting about this first and then doing a rotation, anti-clockwise rotation is equivalent to doing the clockwise rotation. That's what this is saying. So what you can convince yourself then is that, so now that I've given you the idea of what we mean by group operation here, that I first perform the transformations. And what you can show, I write down these relations. So what you can show is that this set of elements with dot representing successive transformations, okay? Is a group. So now you can see what we have is a collection of elements of the group which are quite abstract because it's simply a set of transformations. Because I'm just asking you what are the set of transformations which leave the equilateral triangle invariant. And what I find is that I have such a finite number of such transformations, and any other transformation which leaves this equilateral triangle invariant can actually be written as some combination of these transformations. And just for you, just so that you will, I hope this is there. So I'll just write down those relations and the combined relations. So, yeah, I guess at least some of them I will write down. So R dot R is R prime. You can also check this. What you have seen is that R dot R prime is identity, and this will be the same as R prime dot. Yeah, that's correct. You can also check that if I do first K is same as this. Let's suppose I do K dot K. Let us see what happens. There was my name here. N was this one, right? N maximum 1 So this will be this equal to so if I do now K dot M, what should I do? Two reflections. So if I do M on 1, 2, 3, I get this 2, 1. Now I do K acting on this 2, 1. What will I do? So I have to now reflect about this. So I'm going to take then 2, 3, 1. But what is 2, 3, 1? 2, 3, 1 I got from here. So K dot M is nothing but now. Now let's ask what is M dot. See, when I did M, what I did was I reflected about this bisector. So when I did reflected about this bisector, 1 and 2 got interchanged. When I did A, I reflected about this bisector, so 3 and 1 got interchanged. Now let us do the other way around. First I do K and then I do M. So if I do K, then I'm reflecting about this bisector. So I'm going to get 1, 2. Then when I do M now on this, it's 1, 3, 2. So now I'm going to reflect about ABC, right? So I'm going to reflect about this bisector. So what will happen? I'm going to get now 3, 1. Because I'm reflecting about this bisector. So these two get interchanged. Now 3, 1, 2. So earlier I got 2, 1, 3. So I got this one. Or sorry, 2, 3, 1. So that's why I got it as R prime. But now I'm getting 3, 1, 2. And what is 3, 1, 2? 3, 1, 2 I get by doing it R. So what does this tell you? What kind of a group is this?
Non-abelian.
Non-abelian. So this is not equal to K dot M. So this group, it's a finite group. So it's a finite group of order 6. Okay. And it is a non-abelian. See the order of 2 reflections about these perpendicular bisectors. How you do the reflections or how you do the order, sorry, in which order you do the reflections, it makes a difference. Okay, and what one can construct is, okay, now for these kind of finite groups, it's often very interesting, or it's actually not interesting, it's useful to construct what is called as a multiplication table. So this is an exercise for you people. Please do this exercise. So the way you construct the multiplication table is the following. So you have make a table like this. Okay. And what you do is in this first one, label the things elements like this. R, prime, A, A. And here also you put the same labels. R prime, A, A, A. And then the way you construct the table is like multiply. It's like when it's 2 in school, 2 into 3, 2 into 1, 2 into 1 multiplication table, 2 into 1, 2 into 3, 2 into 4. Here in this case 1, 1 into 1, 1 into 2, 1 into 3, 1 into 4, 1 into 5, 1 into 6, 7. Now since this is the identity element, I should get back to the same. What this means is this, that in the first row, if this is identity into identity or identity dotted with identity gives me I, identity dotted with R gives me R, identity dotted with R prime is this, same vector. And similarly here what it means is R dot I. So you're actually multiplying the order in which you are multiplying this from this with this, or when I say multiplying, I mean the group operation. So the order we are combining is always this with this, the row element with this column. So R dot I will give in R, so I get back here R prime is A. Fine. Now what we saw was what is R dot R? Okay, I did not construct that. I don't think I did this. You can show that R dot R will give you R prime. So when I take R combined with R, we will find that this is R. And we also saw earlier that R combined with R prime gives me an identity. This is something which we have already seen. So this will give me identity. And similarly, what you can do is also I've done K. You can show that K with K. So this diagonal element will be identity. K with K, because if I do two reflections about the same axis, so I have, for example, here I have reflected about K, and again I do a reflection about this. I will again interchange this. So I get back my identity. So that's very clear. So K combined with K will give me identity. L combined with L will give me identity, and M combined with M will give me identity. But R with R is not identity, it's R prime. Similarly, with R prime, we will get as R. So you will see that your diagonal is not simply identity. Two of the elements are actually, one is R prime and one is R. And then we saw that, just now we saw that when I did K with M, what did I get? I got R prime, right? When I did K with M, I got it as R prime. So what you do now is fill up this table. Okay, because why I'm asking you to do this multiplication table is that it will give you an idea about how I can construct, and this also is a good example because I just show you why. So how do I combine operations? And it also is an example of a non-abelian group because you can see we've already seen that K dot M and M dot K are not the same. In one case I got it as R prime, the other case I got it as R. So please construct this table, fill it down. This is called a multiplication table. If you want some practice for constructing multiplication tables, you can do for simpler cases, for Z4 for example, because there it's ordinary multiplication. So multiplication table for Z4 if you want. Or let me do for the even simple one, because usually teachers do for the simplest case. For Z2 if I do. So in that case, I still have only two elements, 1 and -1, and 1 and -1. Here you have 1, 1. 1 with -1 is this, -1. So for Z2, if I do, it is simply this, the multiplication. If I do for Z4, I will have 1, I, then I will get -1 and -1. So let's write it like this. So I'll get I here, then -1 here, and -1. 1 with 1 will give me this. I with I will give me -1. Then -1 with -1 will give me +1. And -I with -1 will give me -1. And then you get I1 with I will give me I1 with -1 with -1. So this way you can fill up the whole -1, -1. Now we can combine and complete the tables. So the reason why we are interested in filling up set multiplication tables is once you have the table, you know exactly what the combinations will do. And even if I have now multiple, for example, if I want to take R prime K, I already know because I know what to do with R prime. I get that element. That element now will combine with K. The answers are Z apple. Now this particular group is in physics we will call this, because now why are we interested in this particular group, for example, is the following. That imagine now that there are some atoms situated at the corners of such a equilateral. And somehow in a molecule, let's say that I have a molecule which is made of some atoms or identical atoms, and they form the corners of such an equilateral. So then what one can show is that this particular group are the group of transformations which leave that molecule invariant. Or more specifically, it is a group of symmetry transformations. So I can do these symmetry transformations on that molecule. So basically I can change the atoms because they're identical atoms. I don't want, that's why I prefer to put AAA, but I'm putting ABC just so that you know which order I'm doing. So I think of an atom here, an atom here, an atom here, and I make these symmetry transformations on these atoms. Please remember they must be identical atoms. And all these symmetry transformations or any combination of such symmetry transformations leaves this molecule invariant. So then after that, we can analyze now the properties of that molecule by analyzing further about the properties of this group and actually even more using the representations of this. Okay, as I said, finally, when we practically use it in our work, we will actually start talking about something called representations. And from a physics point of view, so this is an example of what is known as a crystallographic point group. This also appears, for example, if you want to study, say, the vibration modes of such a molecule. So people have classified. So this really group theory and the study of group theory and its representation is a very big mathematical subject, and it is a very rigorous subject in itself. And it has not just applications in physics and of course in chemistry also, but also in various other cases. And specifically in physics, the classification of this particular group is called as VM. So this group is called as the VM. So this is what is known as the crystallographic point. So this I have introduced, as I said, it's an example, it's one of the simplest examples of a group which we will be interested in from a physics point of view. I'll say a little bit more about this next Monday. But it's also an example where you can see now group elements being made of very abstract things, like transformations which leave a certain object in place. So please fill up this table, okay, the multiplication table. I have already given all the elementary operations for each of them what it does, and all you need to do is work out the rest of it. Now I want to give you another example of an abstract. Consider now, suppose I have so let's say that I have a set of elements. Suppose I have some set of elements. I won't call them G1. Let's call them as E1. Or let's not even call them C1. Let's call them as simply ABC. I have some set. It's an ordered set, ABC. So let's say I actually it as an ordered. It's an ordered triple of some three values ABC. Now what I do is I consider a permutation of this. What are all possible permutations of this? So imagine that I have three boxes and I put these alphabets A, B, C into those three boxes. Okay? So imagine that. Now I want to permute. Instead of putting A in this first box and B in this first box, I can put B. So let's say I have one permutation. What are all the possible permutations of these three alphabets?
3 factorial.
6. That is 6. So can we list them out, all of them? Can we list out all the possible permutations? There are 6, that is correct. So can you explicitly tell me what are the permutations? So I'll give you one example. From ABC, I can go to PAC. Then any others? See, again, it's what you study in your stat micro numerical study. I have 3 boxes and I've got 3 alphabets. I put A alphabet in the first box, B in the second box, C in the third box. Now, nobody has told me that I should put A and B in the first, A in first and B in second. Here in this arrangement, what I've done, I put B in the first box and A in the second box. Now I'm asking you what are all the other possible arrangements. What she has told us is that there are 6 possible such arrangements. So I want you to list them out specifically.
Ma'am, one is ABC, then ACB, then CBA,
ACB, okay, then
CBA,
yeah,
BAC.
that I've already written. BAC.
Okay, sorry, CAB,
CAB, yes. Yeah. One more here.
BCA.
Pardon?
BCA.
BC. Yes. So these are the 6. So basically, from starting from ABC, I do permutations and I can get this. Okay. Now from here to here, if I want to do, how do I go? How do I go from here to here? What did I do here when I went from this to this? I exchanged B and E.
Exchange.
Right? Keeping C fixed. So the whatever was the object in the third box, I kept fixed. I only interchanged the first 2 elements. Right? So from here to here, when I went, I essentially did A to B, B to A, and C was fixed. I'm just writing this. That's what we did. Now, when I went from, let's ask from here. When I went from here to here, what did I do? From the first one to the third one.
ma'am, kept the
Inter.
first element fixed and interchanged other 2.
So here, when I went from here to here, then what we saw was that I kept this fixed, and then I went from B to C, C to B. Agreed? Now let's ask. Suppose this one and this one. This ABC, CBA. What happened here when I went from here to here?
And B was kept fixed and other 2 were interchanged.
So you can see that the way I did this was the following. But from when I went from this to this was from here. In this case, I kept B fixed and then I put A to C, C to D. Okay. Now when I came from ABC to CAB, how did I come? So when I went from ABC to CAB, how can I come?
It was, ma'am, we reversed the order.
Yes.
Sorry. Ma'am, yeah, we have we have rotated the combination.
Yes. So can you tell me how do I do that? Yeah, yes, you're right. I rotated it correctly. How did I rotate it? So can you set up some kind of a
Ma'am, clockwise, in forward direction.
So what you can see is that I have made. So first of all, I went from A trying to B, this position, right? Or if you want, you can say that I can say that B went to A, right? From this segment to here. So let's let it right. So let's rewrite it like this. That here, if you look at this, what has happened? C has gone. This has come here. So because you can see this has come here, right? And then this has gone here, and this has gone here. Okay. So C went to A. Or if I will not put it in this fashion, I just write it like this. C went to this, then B went to C, and then A went to. I'll give a slightly different notation. But you can see that this becomes a little clumsy if I'm using this alphabets itself, because it's already a little unclear. But nevertheless, let's proceed with this. Now, if I go from ABC to this one, BCA, how do I go from here? In this case, how do I?
Ma'am, same operation.
But you're going this way because now I'm saying that C has gone to B, B has gone to A, and A has gone to C. Okay. So what you can see is that okay, so let us look at the differences. That in this case, in this one, and this one, here I kept one of them fixed, I only interchange the other. And in these two cases, I have interchanged all of them. Okay. And you can also see that if you look at this, for example, here, that I have done a cyclic interchange. C went to B, B went to A went to C. Similarly, here I have done a cyclic interchange. C went to A went to B, B went to C. So I can write it like this, that C went to A went to B, B went to C. And now I'm going to give a notation for this. So essentially, what we have done here is permutate three objects. Now, whether I call those three objects as A, B, C or X, Y, Z, it doesn't matter. Or say some other thing, some red, blue, green colors, it doesn't matter, right? What we are doing is actually the operation of permuting these objects. So in the first three cases, this case, and this case, what we did was we kept one of the objects fixed. Whether it was like, for example, here, what we did was when I went from here to here, I kept the object in the third position fixed and interchanged the objects at the first and second position. Here, what I did was I kept the object in the first position fixed and interchanged the objects which were in the second and third position. And in this case, I kept the object at the second position fixed and the interchange was between the first and the third position. And here you can see cyclically I've gone from 3 to 1, 1 to 2, 2 to 3. In this case, I've gone from 3 to 2, 2 to 1, and 1 to 3. Okay. So I will give a notation like this. And we will call this as, so this particular operation, I will call it as like this. Okay. I will give a label for this. So I will say that this is equal to, I'm keeping the third piece. Right? So this I will call as E, which is equal to. So this particular operation. Okay, so this notation, what this notation means is the following thing, that first I have three objects in positions 1, 2, 3. And if I'm keeping 3 here, means if nothing I'm doing here, and in this, which is there in this round bracket, 1, 1, 2. 1, 2 means that I'm interchanging one entry. Okay. So in other words, what it means is the following. That if I take 3, 1, 2, and click on ABC. Okay. So what this means is that 3 will remain the same, and this 1, 2 will cyclically interchange. So A will go to B, B will go to A. So I will simply get. So this operation means that the 3 part I don't do anything, 1, 2 will change side. Similarly, for this particular operation, I will call this as 1, and then I change cyclically I will change this. And I give a label to this as D. Or C, let me call this. And this one is, I will call this as D. So that operation I'm calling this, and in this case, what we are doing is we are interchanging 1 and 3 and giving 2 first. So E acting on ABC. So now I'm giving a shorthand notation is equal to this, and what this actually means is that. Similarly, if I took D, D is by definition 1, 3 and 2, and this acting on, so D acting on ABC will be equal to 1, 3, 2 acting on ABC, And that gives me B will remain fixed and 1 and 3 as a cyclically exchanged I get C. And notice now that, see, this is now just an operation which I'm doing on some set of elements. It could have been ABC, it could have been red, blue, green, it could have been anything else. So once I perform on this, so it doesn't matter whether I have BAC here or red, blue, green here or some other kind of anything I want to do. Any indices I can put there, but I know what I mean by these operations. Similarly, I will give a name to these two. So I have C, D, E here, and then I'm going to here. This particular one, I'm going to call this as equal to A, which is equal to, and I'll call this as 2, 1. Or maybe I'll just call it as 1. I'll call it as 1. Okay. So if the whole thing is in bracket, okay, like one, if it is the whole thing is in circular bracket, this is called a cyclic interchange. So what it means is that 1 goes to 2, 2 goes to 3, and 3 goes to 2. Or if you look at this, for example, here I can rewrite this in the following way: that A goes to B goes to C, and C goes to D. So whatever is happening inside these round brackets is there's a cyclic interchange of those elements which are in those positions. So 1 goes to 2, 2 goes to 3, and you have to keep to that order. 1 goes to 2, 2 goes to 3, and 3 goes to 1. Same thing I get here. 1 went to 2, 2 went to 1. And because this was separate, nothing I get here. Similarly, here when I get 1, 3, I cyclically interchange 1 and 3, 2 I get fixed because 2, nothing I can do. And same thing for this particular case. 1 is kept fixed, 2 and 3 are interchanged cyclically. Now in this case, I'm cyclically interchanging 3 objects. 1 goes to 2, 2 goes to 3, 3 goes to 1. So therefore, now if I look at this, and if I make A upon ABC, so if I take A and then act it now on ABC, it means that I'm doing 1, 2, 3 acting on ABC. And what you can see is that whatever in the first position must go to the second position. So this will go to A, and you get C. This one. Similarly, for the finally, I will write for B. The other one, I will write it as cyclic instantaneous one. This is the last one. And again, you can see that if I have B, and if I take B acting on ABC, is equal to 1, 3, 2 acting on ABC. So this means that B is like saying that 1 goes to 3. So this implies that 1 goes to 3, 3 goes to 2, and 2 goes to 1. Again, it's a cyclic interchange of these 3 objects. So 1 has to go to 3. So that means A will go here. So you will get A here. Then after that, 3 goes to 2. So the C element must come here. And this will come. So what you can therefore see is that now, so I'll write down this now for you. The set of 6 permutations can be written down in the following way. So let me, so let's write down the set of permutations. I have the set of permutations which I can write on these 3 objects. So these are the operations, please remember, 1, 2, and now there is no bracket here, 1, 2, 3, B equal to 1, 3, 2. The round brackets means cyclically I'm interchanging these 3. Then my C was 1, 2, 3 interchange. D was 2 was fixed and 1, 3 was interchanged. And E was 3 is fixed and 1, 2 was interchanged. Right? And then I have the identity, which is simply that it doesn't work. So identity, I will write it simply as 1, 2. So no interchanges. Now consider the set of all such elements. So consider now this set S, which is equal to identity A, B, C. Now you can see this identity acting on. So identity is this 1, 2, 3. This is a notation which we have set up. If it acts on A, B, C, for example, A1 will remain 1, 2 will remain 2, 3 will remain 3. So I simply get A, B, C. You can also see that now if I take identity and A, I will get back A. That means first do the permutation A. So I will get A acting on. So if I take this active on A, B, C, this is going to give me CAB. And then I have identity acting on this, which is simply going to give me C. See, what this tells me is that whatever is in the first position will remain there, whatever is in the second position will remain there, whatever is in the third position remains there. So I just did A acting on this, and A acting on this changed this to CAB. And after that, I did identity, and it doesn't change anything, it remains the same, which is nothing but acting on that ABC. So what you can then see is that the operations, if I combine any two operations, you already also know that if I do two permutations, I will get another permutation, third permutation. So what you can see is that if I take this set and then combine any two of these operations, it will again belong to the same set. The identity belongs to this set. And you can convince yourself then that the set of all such permutations. See, again here I am only talking of the operations. I am not worrying about this objects itself. I don't care about what is ABC, whether it is 2, 3 black balls or 3, 1 red ball, 1 blue ball and 1 green ball, or numbers 1, 2, 3, or alphabets. But the operations or permutations, these are forming permutation. And again, you can see it's a finite group. It's 6 of order 6. And this is called as S3. This is called as S3 actually. It's called the permutation. And in fact, this was a very important group for us in physics. For example, if I want to study in quantum mechanics, wave functions of identical particles, I have a, suppose I have an n particle, let's say I have a 3-particle wave function. Okay. I mean a wave function or system of 3 particles, 3 identical particles. And I want to find out what is the wave function of this system of 3 identical particles. Now you already know that depending on whether those particles are bosons or whether the particles are fermions, my wave function must be completely antisymmetric under exchange, or it must be completely symmetric under exchange of any of the 2 particles. So in fact, what you will show is that the completely antisymmetric or the completely symmetric wave functions actually form representations of this symmetry. So again, as I said, that's the representations. What we mean by representation, I'm still not going to do, but essentially this will be required, as I said. For example, like when you in quantum mechanics, if I deal with identical particles. And again, all right, you can also check for yourself that this is a non-abelian group. And further, I'm going to say, we just now saw another 6 element group, which was that. Just now we saw a 6 element group. When we considered the set of all transformations which leave an equilateral triangle invariant. We listed out that our identity R prime KLM. You can ask, is there any connection between this group and that group? You will see that we can actually find a connection between these groups. And if you look at that, I mean, I don't know, you remember that KLM. So when I did KLM, so I had 1, 2, 3. Under K, what happened? This went to 1, 3. Basically, it interchanges. So your reflections, if you like, are like your CD. The KLM correspond to CDE, and R and R prime correspond to KN. So you can actually find a one-to-one mapping between elements of the group which leave an equilateral triangle on a two-dimensional plane invariant with the elements of the permutation of 3 objects, permutation operations of 3 objects. So here again, I want to emphasize. See, these are very. I mean, now we are really dealing with something very abstract because we are not even worrying about what objects we are taking. We are just looking at some operations, and we are saying that these set of operations themselves have a group structure. So already you can see that this says that I should think a little bit more, because like what she pointed out earlier, that if I have a group with say only 2 elements, now can I find connections with my 1 and -1? And here also I've shown you that this is something which I've come across by saying I'm permuting 3 objects. Now the other group which we just discussed earlier in the class, identity R prime and KLN, was the set of transformations which give an equilateral triangle invariant. But as I said, that there are very intimate connections between the two. So I can formalize this and ask, like we can ask questions about whether I can map from a particular group to another group. In the sense that, can I make a mapping between one group or the elements of one group to another elements, or the elements of another group? Because then what will happen is that if we can do such mappings, if I know one group, or if I know the properties of a particular group, and if I can show that another group can be mapped into this group by some particular operation, then I don't need to study about the new group again independently. I just need to know, if I know already about the properties of the first group, it's enough. So in order to do this, what we will do is we will discuss a little bit about how I can map from one group to another group and how can we define this. So a little bit more formal definitions. So I'm going to now discuss mapping between groups. So suppose there are 2 groups, like G and G can be 2 groups. What this means is that G is a set of elements with certain group operation defined. G prime is another set of elements with some other group operation defined. It's not that you can have the same group operation or the same elements. Now let's assume that I have a map which takes me from G to G. What does it mean by this? What this means is that, so let's find the mapping. Okay? So I've written the follow statement first, but let's write it first. So let phi be a mapping. From G to G. What does it mean when I say that I have a mapping? What it means is that given G belonging to G, then phi of G is some mapping. So this implies that belongs to. So this could be, say, for example, some function or some way of identifying. I mean, I say that if this element, so let's pictorially what this means is the following, that if I have say elements, let's say this is my group G and let's say this is my group prime, and let us say this is G1, G2, some G and C, and let's say that this is G1 prime, G2 prime. Let's call it something, let's say E1, E2, maybe En. Then what this says is that now the mapping is that, say, suppose G1 takes 5. So phi might take me from G1 to this. So I'm mapping this to this. Similarly, it could be that this also will go to the same. This is also possible. So again, G2 is getting mapped to E. Maybe Gn is getting mapped to this. So under this mapping, I have this kind of image. So you can say that E1, E2 is the image of G1 and G prime. Similarly, E2 is also the image of G. So let's say that I have such a map. And now, suppose such a mapping exists, and now, so let there be a mapping. Now, if or G1, G2 belonging to G. Okay. Okay, I will get you what this is. Okay. So now what I'm saying is that suppose you have such a mapping, and suppose that for any G1, G2, okay, so for any pair G1, G2 belonging to the group G, if phi of G1 G or G. Now so G1 dot G2 is nothing but you're combining two elements of the group G, but because of the fact that G is a group, that G1 dot G2 must be some element which again belongs here because of the closure property. And obviously then there's a mapping from this, whatever is the combined element, some mapping is there. And if you can show that that quantity, whatever is equal to phi of G1 star phi of G. See, what does this mean? This is like saying that this is phi of G1 is whatever is come here in G1 prime, and this is an element which belongs here, and phi of G2 is an element here. So if I'm doing the group operation in G, then it's after the mapping, it's equivalent to doing the group operation here. That's what it means. Okay. If this happens, then phi is called the homomorphism. See, what this is telling me is that I have made the images, but when I combine here, then the images are also getting equivalently combined. So the mapping of the combined thing is nothing but the combination of the images. That's what this statement is. So if I have a homomorphism from two groups or between two groups, then what it tells me is that there is a mapping which preserves the group property. That's what this is. And in particular, now you can see that from this definition, you can see that the identity element. So if my phi is a homomorphism, then the identity element here will be definitely mapped to the identity element. How do I say that? So suppose phi is a formless. So let's assume now that I have two groups. Okay. So we will see what is the meaning or what is the strength of this definition. I'm sure you encountered homomorphism earlier, but here we are using it in the form of. So let phi be a homomorphism from G2. Now my statement is that if I is the identity element of G, and I find the identity element of G prime. Then under one other identity of G or identity element of G maps to identity element of G. words, what we are saying is that if suppose phi is a homomorphism, then under that homomorphism, the identity elements map is nothing but the identity element of G, or phi of I equal to is what one is. How does one prove this? If it is a homomorphism, this will happen. I'll show you now how can prove. If I is the identity element of G, what does that mean? So I will show you how this happens. So this is the claim. Okay, this is the claim. So if I is the identity of element of G, what it means is that x times I equal to x, which is equal to I times. Times when I'm saying it means with respect to whatever is the group operation. I don't know what is the group operation, but whatever it is. So what this also tells me is that because phi is a homomorphism, it tells me that then phi of I combined with x should be equal to phi of I star phi of x. Okay. Now because this is because phi is a homomorphism by definition. But what is, but this should be the same as, because we know that I dot x is nothing but x, so this should be the same as phi of x. Let me say that. Okay, I'll do something. Once. Let me just change this. Okay. No. See, because this is an identity element for any G belonging to G, belonging to this capital G, G combined with I is G, which should be I times, or I combined with G. Now, using the fact that it's a homomorphism, phi of I dot G must be equal to phi of I star phi of G, because these are the image. So these phi of I and phi of G are living inside G prime. But this step follows from the fact that this should be the same as I dot G, because I dot G is nothing but G. So this last one is following because of this. This implies this. But now if you look at these two statements, what is this telling me? That phi of I star phi of G is equal to phi of G for any G. Not for any. Because you see, when I've done this for any G here, phi of G can be any arbitrary phi of G belonging to G. What does this tell me? So if this statement is there that phi of I star phi of G equal to phi of G for any phi of G belonging to G prime, what does it tell me about phi of I? What should be phi of I? Are you people getting the idea?
Identity in G prime.
It should be the identity element in G prime. So this, since I'm doing this for any arbitrary thing, so therefore this implies that phi of I must be equal to identity prime. For identity element. Because for any arbitrary G you are doing this. Or in other words, what we are saying is that the mapping of the identity element in G is the identity element in G. And notice for that I've used the fact that phi is a homomorphism. If phi was not a homomorphism, I could not have done this. And similarly, you can also show one more thing. So you can show this that. So I'll write this that if it's a homomorphism, then phi of I is identity prime. This is one. And you can also show the other property that if it is a homomorphism, then phi of G inverse. See, whenever I write G inverse, please remember it's that formal definition that this is equal to phi of G inverse. So that means if I take the mapping of the inverse element of G in the group G, then that becomes the inverse element of the mapped phi of G. So, or in other words, if you think about G here, and this is G prime. So, suppose G is getting mapped to this, some G primes. Okay? And let us say that this is G inverse. Then G inverse will get mapped to something else, say some G tilde like this, or H. Now, what one is claiming is that if your phi is a homomorphism, then this H is nothing but the inverse of G. So, this is equal to G prime inverse. Again, I want to tell you that this inverse is defined with respect to this group operation star, because it is defined with respect to G prime, while this inverse is defined with respect to the group operation dot. But what the homomorphism reserves for you is therefore the group property, the identity under the mapping, as well as the existence of the inverse. And these are very powerful statements. So suppose I have now a homomorphism. So I can suppose when I say I have a homomorphism, essentially what it means is we construct it. Suppose you can construct such a homomorphism between two sets like this. Then we've seen that certain properties are satisfied. And now let us say that I have further restrictions. That means suppose my homomorphism is such that before I go to that. Now, given a homomorphism, I will define something called as the kernel of the homomorphism. See, the homomorphism, by the way, does not restrict it just to groups, it's a little more general thing, because you will be functions or spaces to define this. So, I will define the kernel as, so define kernel in the following way. So K equal to set of all G's, G1, G2, say maybe some set of all G's, such that phi of K equals to identity every K is a G. So you have this group G, okay, and then what we are saying is that suppose you have a set here which consists of G1, G2 like this, in such a way that any element in this set gets mapped to the identity element. So I have this G prime here, this group here, and if all of them get mapped to the identity element here, so G1 gets mapped here, all this get mapped, then that set here, this set K is called the kernel of the homomorphism. You can definitely say that the kernel must contain at least one element. What element should it contain? At least one element, definitely you know. What is that element?
Identity of G.
Identity. So kernel definitely has identity. Okay. Now I write the identity here. So if now the kernel, if K only contains this identity, okay, if K equal to just one element set, then the homomorphism is called an isomorphism. It's known as an isomorphism. So let me tell you a little bit. So if you look at this, now what has happened here is that what this is telling you, for example, so let's assume that there is more than one element. Then it means that the images of two distinct elements, identity and some other element, both are getting mapped to the same. So in general, for a homomorphism, it's not a one-to-one mapping. It is a many-to-one mapping. Okay. But if you have an isomorphism, then so I will do it a little bit less formally. So I will remove this statement. So an isomorphism is something. So an isomorphism is a one-to-one mapping. Okay. So an isomorphism is a homomorphism is a 1-1 from G to G. So in that case, what will happen is that you have G here, you have G prime here. So if one element G1 is here and G2 is here, then G1 will get mapped to something G1 prime and G2 will get mapped to G2. So if I have then two distinct elements here, if G1 prime is not the same as G2 prime, then I know immediately that G1 and G2 are not the same. And mathematically, one can show that in that case, your kernel will become simply having one element, it is identical. So this homomorphisms and or more the isomorphisms are special kinds of homomorphisms. So what these allow us to do then is to construct mappings from two different groups or from groups to other groups. And again, I want to emphasize the group operation on these two objects, on these two, for these two G and G prime may be distinct, may be different, the elements may be different, but this is a way I can get to construct them. Let me give you an example. Okay, now let me consider this. Okay, let us consider this group G to be the set of all real numbers. With the group operation equal. Last time I showed you that the set of all integers with the group operation is equal to addition is a group. I can actually generalize that and show you the set of all real numbers with the group operation defined as addition, ordinary addition, that forms a group. Because you can see that if I add any two real numbers, I will get back a real number. So that's a closure property. Addition of real numbers satisfies the associative law. So the second property is satisfied. And what will be the identity element here?
Zero.
Zero, that's it. And does there exist a unique inverse? Given a real number x, can I have another unique inverse?
Yes.
Yeah, what will be the inverse?
Minus x.
Minus x. Okay, so you can see that this set, so if I call this set as R, is G equal to R, the set of all real numbers, it's the group operation defined as addition is a group. Okay, so let's consider this. Now consider this set. Consider set of all complex numbers with unit numbers. What do I mean by this? When I say the set of all complex numbers with unit modulus, that means it's the set of all z such that when I say unit modulus, what does it mean?
All of them lie on the unit circle.
So but mathematically, what is the definition of unit modulus? If I say that z denotes complex numbers, so what?
Distance of origin is 1.
Huh?
Distance from origin is 1.
How do you write the distance mathematically in terms of z? Given
Root
z,
of x square plus y square is equal to 1.
yeah, but what is root of x square plus y square in terms of z? Because it's a complex number, I denote
Mod
it
of
as.
z.
Huh?
Mod of z.
Right? So this is equal to the set. So let my G prime equal to this. Okay. So all complex numbers with unit modulus, that means fine. Now consider this map. Consider this map phi from G to G. In the following way. So I define formally that phi will take x to e to the power x. So every x. So let me define the mapping formally like this. So if I have a real number x belonging to R, the real number, I define now e to the power of ix, and you can see that if x lies on R, e to the power of ix is obviously going to be a complex number, cos x plus I sin x. So e to the power of ix lies in it. And does this have unit modulus? So given, okay, I guess. So x belonging to R, so it's a real number. If I construct e to the power of ix, by definition, what will this be? Complex numbers, if I expand
Cos x plus I sin x.
cos x plus I sin x. So it's a complex number. Real part, imaginary part. What is the modulus of ix? So what is this?
1.
Without cos square x plus sin square x. This one. So therefore it satisfies this. So therefore, given a real number, so basically what you're doing is the following. That means this is my real line. And I'm taking some point x here. Then I'm mapping this to a point which lies in the complex plane. So this is my complex plane, and it's going somewhere. So this is my Z. So every point here gets mapped. And now, is this a homomorphism? So no. How will I verify whether it's a homomorphism? How does one check whether some mapping is a homomorphism? Or what is the definition for a homomorphism?
The image of the product must be the product of images.
Yeah, very. So in this case, now let's assume that I have xy belonging to R. So suppose xy is belonging to R, then in that case, what I will get is that, so let xy be the points belonging to R. And let us say that when I multiply x and y, there's a usual, sorry, not multiply, addition, x plus y. Let us say I get some term. Because my group operation is addition. So it's x plus 1, I do this group operation.
Ma'am,
Yes.
the group operation on G dash is multiplication, right?
Yeah, that is what. So give the that's give not equal to multiplication. That's correct. On G prime it is multiplication. So multiplication of complex numbers. So I'm writing it explicitly so that there's no confusion. It's understood. Because you can see that if I multiply 2 points on this, I can get again another point here. So that's why this is possible. So verify that this is possible. I forgot to mention that, but you're right. It's very easy. Till 12 o'clock. Because you can see that if Z1, Z2 belong to this set, mod of Z1, Z2 will again be equal to 1. Because mod of Z1 or Z2 will be mod of Z1 times mod of Z2 and 1 into 1. Okay. Now let's consider that I have 3 points here, and the group operation in G is nothing but addition, so it's x plus y. Now let us ask what is phi of A. So phi of A by definition is phi of x plus 1. Okay, so I'll write it like this. Phi of x plus y equal to phi of A. And phi of A by definition is nothing but e to the power of I j. Okay? Because that's what we are doing. So given a real number, it goes to this. Nothing. But e to the power of I, I can then write it as e to the power of I x plus 1. And this is nothing but e to the power of I x times e to the power of I y. So which is nothing but phi of x times phi. So here it is our usual multiplication of complex numbers. See here in the G I have done addition, but you can see here I x plus 1, and here it is multiplication of complex numbers. But you can see that this is again going to be equal belonging to G prime. So it satisfies this condition that phi of x plus y is the same as phi of x times y. If you, in my older notation, phi of x dot y, phi of x dot y inside is nothing but phi of x star phi of y. Okay. So therefore, this implies that your phi is a homomorphism. Now, is this a many-to-one mapping or a one-to-one mapping? Meaning, is this, can we think of this as an isomorphism? Or,
Many to one.
yeah, why is it a many-to-one?
Because if x is x plus 2 pi, then we'll get the same complex number.
That's right. So you can see, for example, if I take the simplest 0, 2 pi, 4 pi, minus 2 pi. So see, any x plus twice pi n will give me the same answer here also. So the whole of this, I mean 0 or x plus twice pi n. So x plus 2 pi n for any n integer gets mapped to z equal to e for all integer. Or this is equal to any integer 0 plus or minus 1 plus or minus 2. So therefore, you can see I have an infinite number of points which are all getting mapped to the same point in the set. But now you can see how to make it an isomorphism. One way to do that would be, let's suppose I restrict my x now. Let us say that, okay, I'm not going to show this, but suppose I restrict my x values to lie only on this. Okay, and then obviously then the group property is not satisfied. Because then what is going to happen? That if I add to, like for example, if I add pi and 3 pi by 2. If I add two numbers which belong here, it will not remain in this set, it will go out here. But if I now do some modulo addition, so if I define now the group or modify my group property also, it is really possible then for me to go from a restricted set here to this set here to make it an isomorphism, but I must also change this step. But I won't get into that. All I wanted to show you here was that I can construct mappings from one group to another group, and as you can see, the elements in one group are different. Here, for example, the elements in G are real numbers, while the elements in G prime are complex numbers. The group operation itself is different. The group operation is addition here in G, while the group operation in the G prime is multiplication of complex numbers. But I can still get a mapping from the set of elements in one group to the set of elements in another group. So essentially what one does is that when you want to relate groups, you actually identify or you construct explicitly such mappings and check whether they satisfy the properties or not. Okay, now I want to show you that the two groups which I introduced today is S3. So S3, which was identity A, B, C, D, E, the permutation group of 3 objects, and the 3M group, which is nothing but what I call as identity R, R prime, K is in. My claim is that these are isomorphic to each. So when I want to show that they are isomorphic, first of all, I must show that firstly there is a mapping between the two. So I'm going to identify the following way. Just for the sake of this, I will say that you identify this with this and identify this with this, this with this, this with this. Okay. And then A and B, we just check. Okay, I don't know which one gets identified for this because I think this is correct. 1, 2, 3, and 3. Because 1, 2, 3, and 3, 1. That's correct. This is correct. Okay. So I make this identification. So my phi does this. That phi of identity goes to this. So explicitly I write down number. So there I give a functional identity. Here we give explicitly this identity. The next thing is, so this is the mapping. So define phi like this. Okay. Next thing is check if phi is a homomorphism. How will I check whether it's a homomorphism or not? Oh, so if I ask you to do this, how would you do this?
Kernel must just have identity.
Homomorphism, I'm not talking of isomorphism. First, I want you to check. I'm not even going to go into isomorphism. I want you to check, first of all, whether it's a homomorphism or not. After that, it's isomorphism.
The definition of homomorphism.
The definition of homomorphism. Yeah, that's right. So, the image of product. So, if I take two elements here in S3, so this is my G, and this is my G prime. So I take two elements in S3, G1 and G2, and this should be the same as phi of G1. Notice that G1, G2 will correspond to one of these, I, A, B, C, D. Whereas phi of G1 will correspond to this. So what you must show is that, so for example, if I combine here B and C, then what you must show is that it's equivalent to combining R prime and K here. Okay. So that is why what I want you to do therefore is to fill up that multiplication table which I wrote down. Okay. So exercises for you is the following. Finish that multiplication table. So fill up the multiplication table for this one. So finish that to complete it. Let me say complete it. I've written down some of the elements, but complete that. And the other one is construct the multiplication table for S3. So here, for example, see when you say I combine A with B, so A with B was like 1, 2, 3 with 1, 3, 2, I think. So you have to write this now in terms in the notation which you have written. You should show that 1, 2, 3 will be one of these elements. So, for example, here I had this was 1, 2, 3. This is 1, 2, 3, 1, 3, 2, and this was C was I get 1 fixed and 2, 3 was there. This was 2 fixed and 1 3 was combined, and this is 3 fixed and 1 fixed. So you must write 1, 2, 3 combined with 1, 3, 2. That means I've done this first permutation of 1, 3, 2 of ABC like that. So add this because you see this is simply an operation. So the best way to do this is that you add this on some set of objects and then figure out what is the resultant operation. Fine. So you construct this. Because then what will happen is once you construct that multiplication table for S3, you will complete whatever multiplication table for 3, and then what you can do is verify this. For any G1, G2, convince yourself first. So convince yourself means you have to look at this and show that explicitly that it really will work out. That for any G1, G2 belonging to G, if I take the image of the product, that will be nothing but the product of the images. Then you are convinced that phi is a homomorphism. Then the next thing is to show that this is really an isomorphism. That is a one-to-one mapping, and the kernel is actually just that. Okay. So verify this. So in this case, therefore, we actually see that, I mean, once I have an isomorphism, it means that if I know about S3, then I know about C3M and vice versa. I don't have to treat these two differently. And this becomes really very useful. So for example, when as I told you that finally, oh, okay, maybe I'll just make a mention of this now. That finally what we are going to study is we are really not going to worry about group elements itself. I mean, when we are really talking about physics, the most important and useful things will be what are called as representations of groups. And what does one mean by representation of a group? Representation theory. It's a very involved mathematical work, mathematical subject, because people have studied this very extensively for various kinds of groups, finite groups, infinite groups, continuous groups, and so on. So essentially what it means is the following, that given this set of group elements, for example here we have these group elements. Okay. When I say I have a representation, what we mean is that I will represent these group elements or I might represent the group by matrices. By actually n by n matrices. I'm trying to give you first just a simple kind of a some kind of a heuristic or a hand waving kind of definition so that you get build up some kind of an idea of what's going on. So I have these group elements, and as I said, often we will not be particularly interested in that element itself, but what we will be interested actually is what that element does to something else, and that what it does to something else we can understand by representing the group elements by n by n matrices. And now this, I will not write it as n, I put it as n by n matrices. So by square matrices of certain orders, and that m can be different values. I can have a matrix m with just one. That means I can just have one element representing the group. I can have 2 by 2 matrices representing the group, 3 by 3 matrices representing the group, and so on. So now when we are representing the group, how does this come in our field? Why are we interested in this, and why does it impact our physics studies? The way it impacts is that, you see, now I have this matrix. So I represented, say, the group element by a certain matrix. Now this matrix you can think of, so for example, let me give you one example. Let's go back to what we've learned in our classes. So there, I've already showed you that the rotation group or the set of all rotation transformations forms a group. It's a continuous group. And essentially the group elements are 3 by 3 orthogonal matrices. But now I'm going to tell you that I can represent the group by sets of matrices which can have order m equal to 1, m equal to 2, m equal to 3, and so on. M equal to 4, m equal to 5. Any integer element. It's not just 3 by 3 matrices. 3 by 3 matrices are simply a natural realization of the group, but I can have other orders of matrices. And how does that help us? It helps us in the following. Suppose I've represented my rotation group by a 1 by 1 matrix. Okay. Now this matrix, what I can think of, so in some sense, when I think of a matrix, I'm thinking of it as an operator acting on something. So on something means what is that something? It must act on some vector in a vector space. So if I've represented my operator by a 1 by 1 matrix, it means it's just one object. So whatever object it will act on, it must also have one dimension. It must be a one dimension. Okay. And what you can show is that, so if I've represented my rotation group by a 1 by 1 matrix, so it will act on a one dimensional object, it cannot do anything. So that object must just remain the same. And since identity must belong to the rotation group, so this representation that 1 by 1 object must be the identity. So identity will act on that one dimensional object. It doesn't do anything. It remains invariant under rotations. So if I go back now and look at what we have defined as a scalar, the scalar is something which doesn't change under rotations. So in fact, it transforms now. So we will say it transforms as a one dimensional representation of the rotation. So a more, what should I call it, a more fancy way of defining a scalar is, I'm not only restricting myself to Cartesian tensors, not the non-Cartesian. So there I will say that the scalar is a quantity. So we defined a scalar as an object which has, it has no index and it has just one component. So now I'm going to say a little bit more that it is something which transforms as a one-dimensional representation of the rotation. Similarly, if you look at the vector now, which is a tensor of rank 3, that has 3 components. So now whatever is the operator which will transform on that will be acting on a metric on a column vector, which will have 3 components, and this will correspond to what is known as a 3-dimensional representation of the rotation. And if I go back now to what we learned in your angular momentum, so the scalar now will correspond to an object which has angular momentum j equal to 0 or L equal to 0. And one can show this. Then your vector will correspond to something which has angular momentum 1, because if you have angular momentum 1, the dimension of that representation will be 2 into 1 plus 1, which is 3 dimensions, and so on and so forth. So, when I talk of representations, as I said, so at the back of our mind, I have this, I'm representing the group by matrices, and these matrices I can think of as operators acting on some vectors in some vector space. And what essentially we are therefore interested in the study of how these objects, or what these objects actually do to certain physical quantities which we are interested in, and classifying those physical objects by properties of this, or what we can see is, like, depending upon the representation, like I told you that the angular momentum quantum number j equal to 0, j equal to 1, that labels now different representations for your rotation. And if I go back to this finite dimension, this particular one here, again we can ask what are the different representations. So one representation you will get, which is very clear, is a 6-dimensional representation in this case. And again here, by looking at the different representations for this particular case, for example, 3M, what I can understand is how the molecular wave functions will transform under this, or I can label or look at how my molecular wave functions will transform when I make these symmetry transformations. And as I said, that these are very important, because if I want to know if the particular chemical bonds will be formed, or if I wish to study about certain vibration modes, or which will tell me about the properties of my system, so that I can extract them by looking at representations of my. And here, for example, this is nothing but the set of symmetry transformations, because we asked what are the transformations which leave my equilateral triangle invariant. So, symmetries of groups, the representations have a very important role to play in our analysis for physics problems. So what I will do, I think, is, okay, I have written down the exercises, please, and I also, while during the class in tensors and other things, I've often told you people to, when I've said that these are certain questions, please do them. So, because your exam is going to be on 31st, so I want to tell whatever I've taught in the class, please work out all those things, complete everything, means exercises which I've left, and any kind of problems which I've written down, please work them out. And by Monday, I think I'll also give you a couple of problem sets, okay? So that you will get some practice. And Monday, I will take one class. So Monday, 11 o'clock, 11:15, because I want to do one more problem. At least touch on one representation. I don't want to start that today formally, but I would like to just touch on a representation of this, at least for the 3M, the point of 3M, so that you get just some picture of what's going on. And as I said, in case if people are interested, then of course I don't mind doing a little bit more in next semester, either for exam, I mean not as part of the exam necessarily, but just as well. But I think that I don't want to complete, I mean I don't want to say finish the course without doing at least introducing you to the idea of what we mean by representation. And I thought instead of doing a lot of theory, what I will just do is simply take one particular example and work out some representations for that. So I do that on Monday. Okay, then I think I'll stop here today. Thank you.